All right. Well, this is a very visual lesson, so that's why I just had to have this one live. There's no way I could adequately communicate this without like doing a real-time demonstration. So I'm like going to be doing special effects in real time. That's why I'm here. Let me turn the light on so you can actually kind of see me. But I've got this whole thing set up so that everything's going to work out. Anyway, I'll get to that in a couple of minutes. I'll let everybody come in.
It's the sun.
Let's see who is. Okay. Welcome, everybody. It's good to see/be virtually in the same place as you. The last time I did this, I kept forgetting to admit people, so I'm going to wait a couple minutes just so I don't leave people hanging outside. How's everybody doing?
Beautiful. Pretty good.
Awesome. Awesome. So I think I sent this out. Here, let me put some light on my face. So I think I put this out in a message earlier. I've got enough space material in the textbook to go for like the whole rest of the year, but like, you know, space is one of those things that everybody likes. You probably have some things that you're curious about. If you want me to cover something, like just let me know. I can probably even work it into the chapters, and if not, I'd rather do stuff that you care about than stuff that the book cares about. So like, you know, whatever it is, black holes, multiverse, relativity, nonsense, whatever, you know, let's make it ours. Got a few more coming in. Hello, everybody who just came in. Hello. All right, I don't want to start quite yet because if more people join and I start teaching, all of a sudden I'm going to forget that there's people and they're just going to be waiting there the entire time and I'm never going to let them in. And that would be sad. Okay. Okay, so I got 15 in here. Oh man, it was I'm trying to remember the total number of everybody. It was 20 something. It kept changing throughout the year, which was good,
Mr. Estes,
Hey, what's up, Andrew?
did you ever see my email about the one thing that you said in the video?
When did you send that?
It was like a couple days ago. You could like answer it like quickly, probably.
Here, let me see if it's here the surface. That's just the kind of thing that I want to do right now. Let me see. Ah, no, I didn't see that. All right, let me see that. Got it. All right, it's a pretty general question. Andrew, do you mind if I read it and answer it right now?
Yeah, no, I don't mind.
All right, yeah, and then when I'm done that, if anybody's still in the waiting room, I'll let them in, then we'll get started. So Andrew asked, the other day in one of your videos, you said that when you enter the thermosphere, it gets very hot, but you wouldn't feel it. How hot is it because of the space between each molecule, air molecule? If this is the case, how do meteorites burn up in the atmosphere? Ah, okay, is it because of how fast they're moving, causing them to collide with a bunch of air molecules, even though they're really spaced out? Yes, okay. Good couple of questions. Yeah, so when we think about things that are hot versus cold, this is one of those scenarios where there's a scientific way of thinking of it, and then there's like an experience way of thinking of it. So we think of things as being warm, as in having a high temperature, if when we touch it, it feels warm to us. The I should say more physicsy, sciencey way of determining temperature actually has more to do with the average kinetic energy of every particle. So if you think about like all the molecules of air in a container, almost like they were just like a swarm of flies flying around, cold air has the flies moving slowly. Warm air has the flies moving quickly. So if you were to, I mean, it's just like giving me the creeps just thinking about a container of flies, but if you were to like expand that container so that the flies have more room to fly in, they can still be going really fast and never hit each other. But in order for you to feel warmth from it, they would need to be hitting you a lot. So having really fast but really spaced out particles means that the temperature can be really high, but it doesn't feel warm. The meteorites, though, they're not getting burned up by that high temperature because when the meteorites feel the thermosphere, it doesn't feel hot to them. The reason that they burn up is because of friction. So if the air molecules are really spaced out in the thermosphere, then they're not really encountering a lot of friction. Whereas when they get down to like the mesosphere and the stratosphere, where there's a higher concentration of air particles, then they're going to be smashing into them more and more. That's what causes the friction that causes them to burn up. It would be no different than like when you're in the pool, you can just wave your hand around, but when you put your hand in the water, all of a sudden it's really hard to move your hand around. Well, I mean, if you forced it and shoved your hand through the water at like 100 miles an hour, it would really, really hurt your hand. So just scale that up to be a meteorite going through the air at like thousands or tens of thousands of miles per hour, and yeah, the friction will just destroy it. Anyway, did that answer your question, Andrew? Because actually, I think we have everybody now that we're going to have, and we can get started.
Yes.
Awesome. Okay. So I have to do a whole bunch of graphical stuff. I want to make sure that this is as visual as possible. This is the kind of thing I just wish I could do on a whiteboard in front of you, but this is as close as I can get. So what I want to make sure of is that everybody can see this screen right here with my hand on it that has this reflection on it. Can everybody see that?
Are you on like is that like a mirror or something? I'm so confused.
Actually, yeah. So
He's sharing his screen with us.
I wonder if I can show that to you without
I
messing
can't see
stuff.
that.
Look it on his.
So I have an iPhone resting on this plastic frame, and underneath that plastic frame is a glass pane, and I'm gonna be doing so. I think this is like last year or something. You know how like there's all these like every movie these days has fantastic special effects in it, and they're all done by computers, and we kind of got used to that. Well, I saw a special effect in a YouTube video like a year ago, and there was like a little explanation of how it was done. There was like no computer in it at all. It was a completely practical effect. I was like, what? So when it comes to visualizing stuff, I mean, I can't do computer animation, but I just want to try to put on a screen something that I could have tried to illustrate on a board. Who knows? But I was testing it out earlier. I like the way it looks, so I think this should be good. I'm going to stick with this light just for now, and then I'm going to move to something else. So, you guys, I think geometry is a 9th grade class, isn't it?
Yes, but
Okay.
some people are in it.
Oh, okay, yeah. I was in geometry in 8th grade. So when it comes to shapes in geometry, usually you're dealing with polygons, though there is a shape that we kind of learn, not quite technically, but we still learn it. Y'all know what an ellipse is? ELL.
Heard of it? I've heard of it, but
Yeah.
All right, so I'm going to actually give you a formal definition of an ellipse, and it actually matters because of this subject matter. So let me see if this works.
Isn't it like
Estes,
an
are we
oval
supposed
or
to see what
something?
you're writing?
Oops. You able to read that?
Yep.
Awesome. Okay.
Mr. Estes,
Yes.
I can only see your face. I can't see what you're writing.
Oh my, what a terrible state of affairs. Let me see if okay, good. This is the kind of thing. Oop. Did I just go away? And are you able to see what I'm writing now?
It's just your profile picture.
Oh darn. All right, let me fix this. There should be a way that I can pin the screen. Let's see how to do that.
wait, I can see what you're writing.
Mhm.
I don't know what.
It's
I don't know why.
possible that so do you see where everybody I mean do you have a place where everybody is over on the side?
Yeah.
I wonder if you're able to go through there to find other people, and you might find where I'm writing somewhere in there.
I
Because
can't
that's really
find
where the
it.
whole show is. If
Well, let me see.
I mean, there's hardly even a point for my face to be here. The only reason that my face is here is because it's less confusing when you see a mouth move and you hear a voice speak.
Yeah, I can't see your screen.
All right, let's see. Are you able to cycle through the gallery to see who else is here?
Yeah.
All right, do you see
I can.
do you see my screen there somewhere?
No.
Let's see.
I don't see it either.
How to do this. Ah, okay. Did that do it?
Nope.
Oh, darn.
Who is Ellie Williams?
It's probably Natalie.
That's Tally.
Yeah, sorry, that's me. My mom was using my phone the other day for Zooms.
Let's see. Oops. All right, let me see what I can do about this. I'm gonna find something. Hold on. Spotlight video. Okay, now what does everybody see?
I still see your face.
Does anybody still see what I'm writing?
I do.
Yeah.
I can see it.
Okay.
I can see you're
I don't.
up in the little bubble, and then you're also big on my screen.
Okay. Huh. I'm not sure what to do about that. The only options I have are to pin or spotlight. Do you still see my face?
Yeah, I think you are pinned, but it's just your camera that's on the wrong thing.
Interesting.
Annika, he's sharing a screen, so it's like different from what you see on his?
Yeah, he's shared with me. I just can't see his screen. It's just his face. The camera's on his face instead of the screen.
Well, that's not what I want. Okay, so yeah, what I'm
Wait,
puzzled
does it
about-
say ellipse at the top left corner of
Yeah,
the
it
thing,
says ellipse.
Monica?
Oh yeah,
Not for
I wonder
me.
what she means by face. if I get my face out of that, if I can. If this doesn't get resolved in a minute, I am just gonna have to go ahead and then post the recording later.
Yeah, you might have to do that.
All right. Well, it sounds like most of you are able to see the screen that I'm sharing, and if that's correct, then I'm just going to go ahead. Is that accurate? If you can see my screen, would you just raise your hand? All right. Well, those of you with video too. All right. So I'm going to go ahead and if this is just like a total bomb because you can't see my screen, I do apologize, but I don't think I'm going to be able to figure that out right now. So, right, I was going to do a formal definition of an ellipse. So when I wanted to draw a circle on a whiteboard and I didn't have a whiteboard compass, there's actually a kind of a cheap way you can do it. Just got a suction cup from a dollar store, and these are my.
Is that a Nerf dart?
I mean, hey, like, it's what I got. So you do that, then you just have to tie a loop of string, and then you can just, well, first of all, I'll get it to stick. Hold on. Might be a little gross if I lick it, so let me just get a little wet. There we go. Yeah, high tech. I got like this space age video conferencing technology, and I'm still sticking a Nerf dart to a piece of glass. So basically, you can trace a circle just like this, right? Almost like it's a dog at the end of its leash, and you can just kind of trace like that. Obviously, I'm going to go off the glass there for a sec, but I have this set for a different length. So that's one way that you could draw a circle. And that is kind of close to the orbit that the Earth has around the sun. However, I need to exaggerate this shape for you to really get the point. An ellipse is similar to a circle in a way that a rectangle is similar to a square, in that a circle is a specific kind of ellipse. So if I stick a second one on there, so now I've got two of these, okay? A circle has one center, an ellipse has two what are called foci. That's the plural of focus. So if I throw that on there, if I trace this now, this is going to give me an ellipse. Well, I might need to make them a little further apart. So I don't...
Mr. Estes, Cameron Licensing is trying to get into the call.
Oh, thank you for letting me know. I knew that would happen. I'd get teaching and then I'd stop paying attention to the waiting room. Oh, yeah, okay. Thank you very much for that heads up, Andrew. Okay, so everybody should be in there now. Sorry, guys, I didn't realize you were waiting. Anyway, I was just about to start using my high-tech art equipment. So using this, if you trace the extent that this will let you go, see, that did not show up quite as well as I would have liked. Does that show up better now? Yeah, you can see that better now, right? So that that almost looks like some weird Ninja Turtle or something. So that shape that was made there by tracing the string around those 2 points is what's called an ellipse. And what's fancy, what's special about an ellipse is that that is the shape that a real orbit is, because 2 different like large masses that attract each other with gravity, they're going to end up circling around each other. we tend to think of the Earth as circling around the sun, and that's not quite technically correct. They actually circle around each other. The difference is that the lighter one moves more and the heavier one tends to stay put. Obviously, the sun is like millions and millions of times heavier than the Earth, which means that instead of having these far apart like that, they're basically right next to each other. And when I do the string thing and trace that, it's basically a circle. But I mean, you know, it's worth noting, at least on a technical level, that the actual shape of the Earth's orbit is not circular, it's an ellipse. And since it is an ellipse, kind of like a squished circle, the Earth is actually a different distance from the sun at different points in the year. So let me tell you what the names of those are. And if you're note-taking, you can write those down. There we go. So when the sun is the closest, I'm sorry, I should say when the Earth is the closest, we call that a perihelion. Peri, you know, meaning close, helion meaning sun, like the Greek sun god Helios. And then when it is the furthest, we call that the aphelion. All right. Does anyone want to take a guess when the Earth is closest to the sun? You just call it out because I can't see everybody to you know, call on you. Anybody want to take a guess when you think the Earth is closest to the sun?
Summertime?
Summertime?
Fall.
Fall?
End
All right,
of
so we got some
summer.
guesses for August and September-ish. Any other guesses?
The summer solstice.
Summer solstice? We would
We're
think
probably
so.
wrong
Yeah, you'd think so. It's actually
because
February.
it's the way it's tilted for us, I
Mhm.
guess.
Yeah, so this is something that, you know, all of us in the northern hemisphere would fall for. It turns out that the perihelion actually occurs in January, and that the aphelion occurs in July.
Wait, is that why it's dry season and wet season? Like, because it's towards the equator? Because that's the part that kind of stays still.
Well, like I think you said a minute ago, that has way more to do with the tilt. The actual distance difference is so minuscule that it has really no actual difference when it comes to the actual climate. So let me just actually tell you what the distance is from the Earth to the sun and what the difference is, and then I'm going to get into what the seasons are and how they work. The distance from the Earth to the sun is actually just abbreviated as what's called 1 astronomical unit, abbreviated AU. And in our imperial units, that's 93 million miles. But the other distances I have are metric, so I'm going to write you that one. It's 150 million kilometers. That's the average distance. So that's really far. That's about 8 light minutes. It takes like 8 minutes and 19 seconds for light to reach us from the sun. That's just how far away that is. So the perihelion, we're only down to 147. So it's a difference of 3 million kilometers. And then at the aphelion, we're at 152, which means the difference is only 3 out of 150. Okay, that works out to be 1 out of 50 or 2%. It's only a 2% difference. So that would kind of be like if you've got a loudspeaker like across a stadium and you like turn your head and your ear gets slightly closer or further away from it, you're not going to get a volume difference from that. So the distance from the sun to the Earth really is inconsequential in terms of the seasons. I mean, if you were to measure a difference, it would be really very minuscule. Instead, the nature of the orbit is going to contribute to the seasons way, way more. So let me set the stage here. Get rid of that stuff. I love how the the highlighter glows, but you know, that was the point. Okay, so I'm gonna set up a little mini solar system. If you'll just give me a sec. Hold on, my son's failing. Not like my son. I mean my S-O-N. S-U-N. Man, it's a good thing I don't teach English. You were standing up for an hour and now you decide to fall over. Okay. There we go. So I need to bring in the sun. So this is going to be our sun. Actually, it kind of looks like the sun. I got some like real lens flare and everything. It's pretty fancy. Pretty extra. Okay. And now the Earth. Ta-da. Oh, my sun went out. There we go. All right. How's the solar system look to everybody? Everybody see that?
Not to scale.
Yes.
I'm sorry, what?
Yes, I see it.
All
to
right.
scale.
So I've got a sun here in the center, and it's very, very bright looking. And then over here on the left, I've got the Earth, and through some really unelaborate stage magic, I have it looking like it's being lit on the sun side. Okay, so I got one marker. Where's my other? Oh, there we go. Okay, see, even at home, I still can't find my markers. Okay, so let's get a little bit of vocabulary here. We have to put our geography and our geology together. So if this is our Earth, you know that the Earth is going to like rotate, and it rotates around an axis. So let me actually like draw a line to represent the axis. It's very hard to work with a light in your face. Okay. So that line, that totally straight line that I didn't screw up at all, that is the axis. And I think I've lined that up pretty well. I've lined up the line that I drew between the light and the dark side of the planet. That's not actually the case. The axis is going to be tilted to this plane of the orbit by about 23.5 degrees. So let me tilt this like that. I'm going to exaggerate this so that it's more visible. After all, I'm working with a pretty small Earth. But all I need to know is that everyone can see the following, all right? That there's a blue ball on the left that's illuminated on its right half, and there is a black line that's kind of diagonal on it that kind of is on the dark side over here and on the light side over here. Is that something that everybody sees?
Yes.
I will take Andrew's yeses and everybody yes. All right, so what we're looking at right here is the summer solstice in the northern hemisphere. And just so that we can get some geographical perspective, I need to draw a couple lines. So first line I'm going to draw is the Arctic Circle. Okay, so the Arctic Circle should be a circle around the North Pole. I think that should be fairly well illuminated. All right. So that would be the Arctic Circle, like, you know, up at the top of Canada, the top of Alaska, the top of Siberia. And so if I put that back on its little pedestal, let me get this back in focus. There we go. Okay. Hopefully you should be able to see. I zoom in a little bit even. Whoop, come on now. The entire circle is in the light side. Can you see that? That the back edge of that circle is on the back edge of the light. Is that something that you see? My entire red circle is illuminated because it's leaning towards the sun.
Yep.
All right.
Yep.
That would be the case on the North Pole, actually within the entire Arctic Circle during the summer in the Northern Hemisphere, because I can rotate the Earth. Oops, hold on. I lost the Earth. Yeah, that would be bad. Let me hold it instead of try to spin on that. So I can rotate this, but the Arctic Circle never moves away from the sunlit side. So during the summer in the Northern Hemisphere, I erased some of the axes. The Arctic Circle is going to remain sunlit 24 hours a day. Okay, so let's do a little bit more geography. You'll notice that I've accidentally erased some of the axis. Let me fix that, because that's going to be important. Okay, so you will notice that if I were to draw a straight line from the sun to the Earth, it would follow a line like that. However, the equator is here, which means the sun is not actually shining directly on the equator. It's shining on a point right there. That is the actual line that is getting direct sunlight. So if I just draw a circle like that, I've got basically a summer equator. Does that make sense? That if the axis is tilted over and the entire Arctic Circle is lit, that the actual middle of the planet is dipped down below, and the new, middle of the planet is kind of north of the equator. That's what the tropic is. And let me make sure I don't screw this one up. There we go. Yeah, that's called the Tropic of Cancer. So in the Northern Hemisphere, we've got the Arctic Circle, the Tropic of Cancer, and then the equator. And this would be on the summer solstice, which is June 21st. In fact, if you look it up, depending on where you look it up, you can actually get it very specific. It'll tell you what time the summer solstice is. Okay, so far we've got the Arctic Circle, got the Tropic of Cancer. Okay, let's move through the year. Obviously, the Earth is turning, but it's also going around the sun, and that means that it would be kind of doing something like this. All right, so let me take it all the way to the other time of year. Now I need to move my artificial sun. All right, there we go. Okay, so now I've got my Earth lit from the other side. Let me rotate this so that my lines are actually visible now. So it's actually kind of hard to see because it's in the dark, but that's actually the point. To see the Arctic Circle here? Actually, is that covered up by something on the right side of your screen? Do I need to move this to my left? Because on my screen, that's where the gallery is, and I don't know if that's blocked for some of you. Are you able to see this over here on the right?
You can kind of just move the
yeah, let me see left.
Well, yeah, it's We could have just moved the
Oh, okay. Well, I don't know if everybody has that option. As long as I didn't just screw it up for everybody, I'm just going to keep it where I've got it. There you go. Turn the sun back on. Okay. So we got our Arctic Circle. We're still tilted this way like we were before. Okay, the Arctic Circle is now over here. It's completely dark. The edge of the Arctic Circle is at the edge of the night side of the planet, which means halfway around the sun, we are now at a place where the Arctic Circle is in 24 hours of darkness instead of 24 hours of sunlight. What time of year do you think this is? If it's half
winter.
After summer, exactly. This would be winter. So this would be on the winter solstice. And if I were to continue these lines around, now we've actually got the equator north of where the sun is shining. And there is this point right here, which is kind of like the new equator. And that is the other tropic, the Tropic of Capricorn. Let's see if I write that here, if it'll be visible. Yeah, it's barely visible. Goodbye, Earth. Okay, you've heard of those terms before, right? I mean, those are like on every map, Tropic of Cancer and Tropic of Capricorn. So let me turn on the overhead light real quick and turn off the sun. Even though that leads to the death of billions, I'm just going to turn the sun off here. Okay, so I've had the Earth partially illuminated. We're going to be looking at the Earth from the sun's point of view for a second. Okay. So this is the equator. Up here is the Tropic of Cancer. Down here is the Tropic of Capricorn. During the summer solstice, the Earth is leaning towards you, and you can see the entire Arctic Circle. Y'all can see the entire Arctic Circle, right? And this Tropic of Cancer is dead center. That's what those lines on the map mean. Alternately, during the summer solstice for the southern hemisphere, the winter solstice for the northern hemisphere, the Arctic Circle has disappeared. You can no longer see the Arctic Circle. It's out of sight. Remember, we're looking at the Earth from the point of view of the sun. The Tropic of Capricorn is now dead center on the Earth. And if I had drawn it, that's a terrible circle. You'd be able to see the entire Antarctic Circle. Okay, so I know this kind of looks like a, I don't know, this looks like some weird face or something now. But what we're looking
It's like a six-pack.
Are different lines of latitude that all just have to do with, remember, the Earth was tilted in the same direction the entire time. It's just that depending on where it is around the sun, it's either leaning towards it or away from it. So when the Earth is tilted toward the sun, it's summer for the northern hemisphere. When the axis is tilted away from the sun, it's winter in the northern hemisphere and summer in the southern hemisphere. And while that might be common knowledge, what might not be common knowledge is that in the northern hemisphere's summer, the entire Arctic Circle is visible to the sun, meaning the entire thing is sunshine all day long. And the Tropic of Cancer becomes the new equator. 6 months later, you've got the Tropic of Capricorn is the new equator, which basically means the equator, when I say the equator, I mean where the sun is shining directly onto the planet, it drifts back and forth between the Tropic of Cancer and the Tropic of Capricorn. So there is something that will happen on the Earth in only these locations. And that is that the sun can actually be shining on you directly overhead. Do you guys know about what latitude we live in Pennsylvania? It's about 45 degrees, which puts us here somewhere. Okay, so I just get the sun back here real quick. Sun. So if we are here on the Earth, but the sun is shining along that line, the equator can get it directly, the Tropic of Cancer can get it directly, the Tropic of Capricorn can get it directly, but we will never, ever get it directly. It is impossible for the sun to shine directly overhead in Pennsylvania. However, if there wasn't like a travel restriction in place, if you wanted to go down to like Florida or Mexico or Texas or something for June 21st, you could have the sun directly overhead. Any questions about that before we move on? I will take the silence as a no. So I went straight from winter to summer. I skipped a couple seasons, didn't I? Yeah, we still have fall and spring to deal with. So let's take care of them. So this one is a little harder to visualize with this, but I am going to try my best. Let me get this back in focus here. Okay. So we've got Northern Hemisphere's winter here. Northern Hemisphere's summer here. Summer, fall, winter. So fall here, you're looking at the Earth, but only the night side of it. However, when it rotates around, it's going to look the same, which means that the sun should be shining directly on the equator on the fall equinox, and that the northern and southern hemispheres should be getting the same amount of sun. And that doesn't matter whether that's on the day side or on the night side. When we go past winter, and it's actually like behind the sun, well, same deal. Okay, that light is misleading now. Same deal. Same amount of sun for the northern and the southern hemispheres. Okay, there was something I wanted to mention, and now it's slipping my mind. Oh, right. So this will take just a little bit of sketching to make clear, and then I can maybe make this a bit less visually crazy. Let me turn off this flashlight. Okay. So let me get my imaginary sun back here. Get rid of this text. That looks so cool. Okay, so for this one, I need a slightly larger surface of the Earth, so I'm going to sketch it. Let me get that back in focus. Come on. Can't you focus? It's like I'm trying to get the whole class up with their glasses on. Oh, come on, camera. You got to know how far away the thing is. All right, let's see if that keeps it. So we got our sunshine. And here is the round surface of the Earth that it's shining on. Because the sun is so far away, all the light that reaches us is basically parallel. obviously this picture is not to scale. Okay. So what I'm looking at here is sunlight from a very, very distant sun, all shining on the Earth, mostly parallel. Okay, so I tried to space these out fairly evenly, vertically speaking. So take a look at how far apart two rays are down here. They're fairly close together. Okay, now let's perform a little geometrical transformation. If you live at this latitude, this is how you're seeing the sun. First, you'll notice it's at an angle. Isn't that the way the sun is when it's like wintertime for us? It's never really high up in the sky. It's always down really low. Once you start driving, you will notice just how far down the sun goes because it makes it impossible to see. Anyway, so this was the distance that separated two different rays of sun around that area. Look how far apart these two are. The actual distance you'd have to go from there to here is a greater distance than from here to here. Really, all that means is the light is more spread out over here. There's, obviously this is just an illustration, but there's two sunbeams here for thousands of miles, where two sunbeams here were good enough for just a couple hundred. The idea is that the further away you get from dead on, the more spread out the sun is. That's why it's cold in the winter. It's not cold in the winter because the Earth is further from the sun, and it's not cold in the winter because there's like more night. I mean, that does matter. There is more night, but really what counts is because of the way the Earth is tilted, a particular hemisphere is either getting more direct sunlight or less direct sunlight. That's what causes the seasons to have their different temperatures. Does anybody have any question on that? Anything at all? Okay, well, that is all well and good. So here's what I'm going to do now, because I know that Zoom fatigue is like for real. And also, that was dumb, and I don't know why I just said that, but there is going to be more like, you know, complete textbook material stuff coming tomorrow. But I have just one like basic question to ask you as a homework assignment that's based on this. And once you get that question, if like your head's about ready to fall off because you've been staring at a screen for like 50 minutes and you can just skedaddle and be done. If you want to hang and work on it and just, you know, chit chat, that's good too. So here's the question. So we know that we know that the Earth travels around the sun in an elliptical orbit, but it's nearly circular. It's nearly circular. And we do have a formula for the geometry of circles. So let's just say we got the sun out of focus, of course. Oh, cameras. So we got the sun and a almost circle around it. This is the Earth's orbit. And the Earth has a radius, the Earth's orbit has an average radius of 150 million kilometers. If the formula for the circumference of a circle is c equals 2 pi r, you should be able to find the actual distance that the Earth travels around the sun, and given that that whole trip takes 1 year, you should actually be able to calculate how fast the Earth is going around the sun. Velocity is a distance divided by a time. If you just did 150 million times 2 pi, you'd get a circumference, like a total distance around the sun that the Earth goes. And if you divided that by 1 year, you'd have it in a unit that nobody uses. People tend to use kilometers per hour, although if you prefer to use metric, the imperial units, because you're like a honest to God red-blooded American or something, you can use 93 million miles. Mil and mile kind of sound the same. Anyway, it's your choice about which one to do. I'm going to write this problem out in more detail on the LMS, so don't fret if you didn't catch that. If you are just totally done with looking at a screen, you can say goodbye and just log out and go, wash your face or something. But if you want to hang out for a minute, work on it, and chit chat, I'll stay here till 3. All right, class technically dismissed.
Mr. Estes, may
Yes.
you please send the recording of this to me if you're not already sending it?
Yeah. After the class stops and the recording, processes, then I'm just going to upload it to YouTube and put it on the same playlist of all of our Earth Science classes.
Mr.
Okay.
Estes?
That way you can refer back to this, if there's something missing from your notes or...
I wasn't able to see it, so I'll
Okay,
just
I am so
rewatch
sorry.
it. It's okay.
Mr. Estes, will this question be on the LMS?
Yes. Yeah.
Wait, so what exactly do you want us to do for the question?
Okay, I just want to know approximately how fast does the Earth move around the sun in this orbit? The way that you calculate a velocity, a velocity is equal to a distance divided by a time. This equation gives you a distance, and we just know it's a year. So if you just did 150 million times 2, that's 300 million times pi. Yeah, it's a big number. Pi is a weird decimal. You have a huge number that is this distance. And then if you divide that by 1 year, you have a speed of huge distance per year, which is technically correct, but it's not very interesting or useful because we tend to use units like kilometers per hour or miles per hour. So I just want you to find the distance, convert years to hours or something, just figure out how many hours are in a year, and do distance divided by time, and then just be kind of weirded out by how huge of a number it is and how fast the Earth is going.
Wait, I'm confused. How do you find, what is the radius?
The radius is 150 million kilometers or 93 million miles. Remember, the actual Earth's orbit is elliptical. However, an ellipse is close to a circle, particularly this one. So the formula for the circumference of a circle will do. You can use 2 pi r to find the approximate distance that the Earth travels around the sun. Remember, it's only like a 2% difference. So it's 2% wider and 2% shorter.
Wait, does that say 93 million miles?
Yes. Yeah.
Okay.
So it turns out writing with a highlighter on glass is not quite the same thing as writing with a dry erase marker, because the highlighter just kind of congeals. By the way, if you're curious, yeah, there's a black light under there illuminating that highlighter. There might be a better way to do that, but I think this almost worked okay. Yeah, so this has become illegible kind of quickly.
When do you think this recording will be available to look at?
It should be up later today. I've recorded a Zoom meeting before. It took like about as long as it takes to save an hour-long video file, which I have been saving a lot of hour-long video files lately. So I think that might take 20 minutes to process, and then another 20 to upload. So it should be up in an hour, assuming that
Okay.
I keep
doesn't happen.
I keep finding the circumference, but then my thing is so like disproportionate. Like I divided the circumference by 365
So that would be
per day, and then I did divided by 24
per hour.
to get per hour. And then should I do per minute or per hour?
Well, you can. I mean, like bullet speeds are usually measured in like feet per second. So really, it's up to you whether you want to have it be like miles per hour so you can compare it to cars, or if you want to have it be miles per second just so it's like, you know, even more face-meltingly fast sounding.
But I keep getting like in like 1 or 2. Like I did the kilometers and it's get like 1 mile per day.
Yeah, I think that 1 mile per hour would not be right.
Well, it's 1 mile per day.
Oh no, that can't.
Do I have to multiply it?
365 miles around. Let's see. So I wonder if this isn't a order of operations calculator thing. So you got a huge number for the circumference, right? It was like unbelievably huge.
2 pi, I'm going to do in kilometers, times 150.
Oh, that's the problem. It's 150 million.
I mean,
So
I don't know what I'm thinking.
Answer of 1.
Wait, no. I think I don't know what I was saying.
Wait,
no, but then I could just, okay, wait. I need to, I could probably do 150, but then I just have to multiply it by however many. But I'll just do it 150 million. I don't know what I was thinking.
Man, I got to use that for something else. Highlighter glowing in Windex. Yeah, just in case you're trying to set this up, just remember that a velocity is equal to a distance divided by time. We're going to get our distance from a circumference, or an approximation of our distance from a circumference, which is 2 pi times the radius of the orbit. And if you're using metric, that's 150 million, for crying out loud. And if you want to use miles, you just change 150 to 93. That's going to be the circumference. And then when it comes to the time, it's just a matter of the units, because, yeah, 1 year, sure, but that's boring. How about 365 days? But we don't usually measure speed in kilometers per day. Maybe you want to change that to hours, but I don't know off the top of my head how many hours are in a year, because it's too many. Let's see if I can fit that in here. I can almost fit it in there. There, how's that for legibility?
Should we just like send you the answers when we're done, like over email?
Yeah, that'll be fine.
I'm still confused what to do.
You're still confused about what to do?
Yeah.
Tell you what, I've got 3 lines up here. Is there a particular one of those lines that's the problem, or is it putting them together?
Putting them together.
Got it. Okay. So if you know how to do this one, that becomes the top of that fraction. And if you can figure out how many hours are in a year, that becomes the bottom of the fraction.
So is this all the information we need?
Yeah. The only information you need is how far it goes and how long it takes.
Okay.
I know this is kind of like a physics question, but I mean, it's either we have you do a basic travel time problem or we have you do astrophysics. So, we're going to go with travel time.
Should
So
we
wait.
email our answer to you?
Yeah, that'll be just fine.
Okay.
All right. I haven't checked the chat like the entire time. I haven't been missing anything, have I? Okay.
So
Yeah,
wait.
you're allowed to leave. If you like, you're technically dismissed. So I think I'd better save those speeds just in case.
Hi, Mr. Estes.
Hello.
Wait, can we change the one?
Can you what?
Can we change the 150 million to 93?
Yeah, you could make it be in miles per hour. That might make the answer make more sense too.
Okay, all right. Mr. Estes.
Hey, what's up?
So wait, it's distance. Well, no, it's time? How long it has to go around the sun, right?
Yeah, which is a year. It's
Yeah.
just that we don't usually measure speeds in miles per year. We usually do it in miles per hour. So if you could change years to hours, you just have to multiply by 365 and then by 24 to figure out how many hours are in a year. It's a lot of hours.
Yeah.
But that should make the answer slightly less like apocalyptic.
Okay.
So, go ahead, Carson.
No, you can.
For the actual problem,
Mm-hmm.
I'm confused. Those are the only numbers that we need, or do we
Yes.
need other numbers?
Yep, those are the only numbers that you need. I know it's tempting to think that you need more numbers because you think this should be a harder problem. This is just a travel time problem that you. Oops. Oh well, so much for that. This is just a travel time problem that you could. I mean, you could give this problem to a sixth grade math class. It's not that complicated. It's just the numbers are big and intimidating, and also.
And so the 150 million, I think that is.
Mhm.
Is that what unit is that in?
That would be kilometers.
Okay.
So if you use 150 million, your answer is going to be in kilometers per hour or whatever. And if you use 93 million, it's going to be in miles per whatever.
Okay.
I should have had this light here the entire time. Well, this is the sun, so I couldn't. All right. Well,
So,
it's
what
3:01. So unless you've got like a last second question, then we can all just bid each other adieu.
So what will we be doing with this tomorrow?
Okay. So the questions for tomorrow are going to be a bit more detail oriented because it's going to be like more textbook content. The purpose of this was to be able to get you to visualize stuff, because the way that we look at maps, it's like two-dimensional. And so when you see Arctic Circle, Tropic of Cancer, Tropic of Capricorn and all that stuff, it makes geographical sense to us because we're like, yeah, the equator's hot, the tropics are warm. But to get like an astronomical sense of the meaning of it, you have to see it. So there's not much I can ask you about this other than Earth round, go fast. Not a whole lot. So tomorrow I'm going to be giving you one of those overviews of the chapter, and you'll have like reading comprehension questions just to make sure that you picked up on the details before we move on.
Oh, okay, so that's what we'll take notes on.
Yeah.
Okay.
Yeah. So the point of today was so that when you do the stuff tomorrow, it'll make sense instead of be like, huh.
Okay.
For the bottom time problem, are we
That
finding
just went away, didn't it?
hours in a year?
Yeah, that should be a lot of hours, but yeah, that's what you'd want to do. Figure out how many hours it is in a year.
And then is
So,
that multiplying times 365?
Yeah. So if you did 365 times 24, that should give you the number of hours in 365 days.
I looked it up to your aid. It's 8,760.
That's a lot. 8,760. Man, that's a lot of hours.
And then you divide the distance by the time.
That's right. Doing the math on that real quick. 8,760. Let's see.
Should I say what I got in my calculator? Because I don't want to like do people's work for them.
Yeah, sure.
Okay, so I got
Is this for the final velocity
107,000.
or for the number of hours? I'm sorry to interrupt.
This is for the velocity, I think.
Okay, go ahead.
I got 107,588.7895. That's what I got.
I think I have the math.
Annika, I got that too.
Yeah, that's right. Yeah, it's a 6-digit long answer that starts with 1. And depending on how you round and stuff, you could end up with that.
And
That is fast.
Is that the answer we need to submit to you?
Yep.
Okay.
Yep.
Okay.
All right. Well, unless you have a last minute emergency, hold on, wait a second, Mr. Estes kind of thing, then I'm just gonna say have a nice day and close the class.
Okay. Bye.
All right. Bye bye.